Well, good morning. Since last time we had an overview over the practical construction methods, mainly for the beam of a cable-stayed bridge. We want today go into the details of how to do the calculation of forces and deformations during each construction stage. This so-called construction engineering is the most interesting and the most important, and in some way, I'm afraid, a little intricate, a little difficult calculation of cable-stayed bridges. We start by designing a cable-stayed bridge in its final stage. But to build the bridge, we also need to know how it's put together under especially 2 points of view. On one hand, we must ascertain the safety during construction at each stage. The beam must not break off because we have suddenly too big loads. And in addition, we want to end up with the desired final stage, so we have to check whether the forces and deformations in every construction stage are those which we have calculated in the construction engineering, and if necessary, we can correct. So, once we have the bridge designed, we have it sized for the final stage. The amount of post-tensioning, say, or the plate thickness for a steel girder is given. And now we must have a trade-off between straightforward, easy construction methods, which may require additional strengthening only during construction, because these simple methods may put more strain on a bridge than in the final stage. So additional cost for strengthening versus more intricate, smaller steps in the construction, which may then permit to go along with the, say, sizing in the final stage. That's always a trade-off. Simple construction methods may require additional strengthening. Additional strengthening may be avoided by using more intricate, smaller steps of construction engineering. And that is a decision basically the contractor, who in a way has to pay for that. I mean, the client finally pays, but the contractor has given a fixed price and he wants to do well within that price. But he will always do it in collaboration with the engineer, because the intricacies, the contractor says, I want to use this type of equipment, I have this type of derrick, doesn't cost me anything, it stands in my yard. And then the construction engineer says, very well, what's the weight of that thing? What, 200 tons? I have only allowed 100 in my construction engineering. If we use your heavy derrick, then we need to strengthen the beam. Cost you so and so much. And then coming back, well, maybe I hire a lighter, then I can. So these are the discussions between the practical contractor, how to put it together, and the engineer who either proposes a way or who shows the consequences of the proposal by the contractor. That is how to start thinking and finding out a way to put that thing together. Now, the construction engineering cannot be done with those simple methods we have looked into for the final stage to do a preliminary design. Of course, we can do some with a thumb, some preliminary checks, but the construction engineering has to be done with a computer system. We need the precise values, we need the precise deformations. So what I am going to show you here are the loadings we use. What are we going to tell the computer what to do in order to arrive at the forces at the intermediate stages. An important difference to the usual calculation of the final stage, as we do for all bridges, is for the highly indeterminate system of a cable-stayed bridge. You remember, in a very rough first approach, the number of statically indeterminate is equal to the number of cables, roughly. So we very soon come to 20, 30, 40 times statically indeterminate. And you know, we are free for every statical indeterminate to choose one action force. We know, I've shown you that for the concrete bridge it is efficient to use the run of moments of a beam which is rigidly supported at the cable anchor points. I've also shown you that for a steel bridge we'd rather choose a different run of moments because that doesn't creep away. And this different run of moments in superposition with a plus-minus life load moment shall give me a minimum amount of quantities for the steel beam. So we are free to choose some run of moments. The only thing we really know when we start construction engineering for a cable-stayed bridge is the final stage after shrinkage and creep. That's what we have calculated. That was our the way we have sized cables and so on. But naturally we do not know the intermediate stages, and unfortunately we do not know with what force or length we have to install a stay cable when we have a cantilever built in a new stay cable. We can make some assumptions. I could give a long discussion on that, but we do not know. The only thing we know is the final stage. And because of that, we come to the, for you, certainly surprising and interesting point that we do the construction engineering for a cable-stayed bridge backwards. That considers a little thinking, getting used to it. But as we know, the final stage, we dismantle it, I show you how, and then when everything is built off, taken off, every action force must be zero. If there's something somewhere in the air without a beam, there is a moment left, we've done something wrong. So we know the end and we know the beginning. And I remember in 1976, early 1976, I was 30 then and I had done something on the Pesco-Kennewick Bridge in Stuttgart. Professor Leonhard sent me alone to the United States to do the construction engineering for the Pesco-Kennewick Bridge, which was a world record concrete bridge at that time with all sorts of respects. And I hadn't done it before. And I knew the only one in my office who had done it, because he worked for a contractor, Hein Lehmann, before, was Dr. Rainer Saul, and he was doing cable-stayed bridges and bridge in South America and Argentina. And so I asked him on one way, when he went back and forth between Buenos Aires and Stuttgart, to come via close to Seattle, this Pasco-Kennewick Bridge was. And he came, and we were sitting down one afternoon. He didn't have much time, 2-3 hours, and he explained that, what I'm trying to explain to you now, very briefly, and then said goodbye, good luck. And I had to do it, and with very limited computer systems at that time. Strudel isn't a program which is really fit for cable-stayed bridges, but that's what all we had. And the numeric preciseness wasn't all that. So we had to do the all-important final stage by hand. And then Strudel couldn't add up changed systems. The system changes from one construction stage when we dismantle it to the other. And Strudel couldn't add up different systems. So by hand we had large sheets with all the shear moments, normal forces, and adding up one system after the other. But at the end everything was zero, and on site they didn't have to re-stress the cables at the end, because there's always a little point of honor that you come out exactly where you want to. So everything worked well, and so I know your situation. It sounds very strange, and but you get it better told than I was told at that time. And when you have to do it, you will start thinking by yourself, and then you understand what it means. Now, we go today by the construction engineering by system dismantling. We have to start and then go back. We have different systems. We can do it with a floating crane. That's very easy because it doesn't put any loads onto the beam. So that's very simple. We can do it for a single system, a little bit more complicated for a symmetrical system. Then we use what we normally use, a derrick. Makes things a little bit more complicated. And then I show an example for the construction engineering forward on site, backwards calculation-wise, forwards in the construction manual where the results of the construction engineering are listed, like recipes in a cookbook. Thou shalt do this and that and check this. That's the first part. And then we come to a little unfortunate thing. If we have auxiliary systems, especially auxiliary stays for the tower, auxiliary piers, then our backwards method doesn't work immediately, because offhand, in the final stage, it's not there, the auxiliary staying. So we do not know, by going backwards, how to install this system. So there we have to put in a little additional calculation, first going forward, finding out what the forces will be when we take it out during real construction. And then these forces we have to introduce when going backwards. That's a little complication. So we go through these things, and then in addition, to complete the picture, we may have to support the derrick, traveler, whatever, during construction, because it's too heavy for the beam to carry the cantilever cable distance long. And there are also various ways to tie it back and to calculate it. So I'll show you the whole picture, and once you have to do it, you'll have to think about it again, but you get at least an idea. Now, when we have somewhere concrete in a bridge, we have some shrinkage and creep between what I call T = 1, opening for traffic, to t equals infinity after shrinkage and creep. So what we have to do when we start with the final stage, which is always after shrinkage and creep, and we have, like here, we take the Mannheim-Nord bridge as an example. We have a concrete approach and a steel bridge. So there is some shrinkage and creep in the concrete part, which we apply negatively, which you can either do it in a computer, you simulate the deformations by temperature loadings, that's the old-fashioned way, or you just take shrinkage and creep with a negative sign, and then you get against the final stage, you get certain moments and normal forces due to negative shrinkage and creep. And also we have to take off the superimposed dead loads, SIDL, Ausbaulasten G2. In English are SIDL, superimposed dead loads, which means asphaltic concrete, traffic railing, lampposts, things like that. So that we take off the bridge and then have our starting system, which we have to dismantle structurally. And we do it first, the simplest there is naturally. We do it with a floating crane, which means there's some air hook to which we can hang the system, and it doesn't load our beam first of all, but rest assured we will then come to the derrick. And we also start with a single tower system, which is the simplest, and then later go on. Now, here we have our bridge at t equals 1, without or after shrinkage and creep and superimposed dead load. That's taken off. And now we have to structurally dismantle, thinking-wise, this system. Now, I tell you the load cases you are going to tell the computer, and then you use Sophistic or TDL or some appropriate system who does it. I'm not going into that, you know that much better than I do, but I can tell you the loadings you have to apply. So, the first step for dismantling is that we apply a pier settlement of that size that the support reaction here under permanent loads becomes 0. Then we take out this support from our structural system, and then we have the next system which just has a cantilever here but no support anymore. Then we remove the dead weight. That's all there is. We have taken shrinkage and creep and superimposed dead load out. We remove the dead weight, means we apply it with a negative sign if that's easier for you to think. Okay, then all that's left is here a weightless cantilever, which means we have here at this point the 3 action forces, moment, normal force and shear 0, which means we can just take out of our computer system this part which has no action forces left. Then, next step, we elongate this cable by such an amount that the cable force under this permanent load stage becomes 0. Elongating the cable, you understand, in Germany we would say, for example, spreizen. The cable is cut and it's lengthened, and the condition is lengthened by such an amount that the actual cable force we have at this stage becomes 0. Once we have done that, we can then remove the cable from the computer system, just taking it out, because it has no force. We can only take out something which is forceless. I think that's understandable. And so pier settlement, Support reaction 0, take out the support. Cable elongation, that cable force is 0, take it out. Then again, then we can take out the cable. Go on, having here again the cantilever. Remove the weight of this cantilever and take out the cantilever. So, then we have arrived at this stage. Now, we elongate, we can do it one after another, we can do it at the same time, the two remaining cables in such way that the cable forces become 0, then take out the cables. Now we are left with this system, cantilever and approach beam and tower. Now we take off this cantilever weight and remove the cantilever. Finally, we take off the approach weight, take off the approach beam, remove the tower, and finally, if you want to do in order to make it perfect, take off the supports, and what is left is no system, and all action forces compared here from the beginning have meanwhile become 0. And that's the governing condition. So what I've shown you here, and it's the most simple way to do it, that is the heart of construction engineering. I have not lost a word about, for example, what the size of this moment here is. That's the next step that we check. Can we take the action forces which occur from this type of dismantling? Until now I've just shown you how can we reduce the system so to that stage when we begin on site. And naturally I then have to check every intermediate stage. Is the moment at the cantilever, say, not bigger in plus or minus than in the final stage? Is the sizing of the final stage sufficient for this? Or is it not? If not, I have to do either I have to reinforce the beam or I have to use a different construction method. But this is very important, whatever we are talking about later refinements. This is it. That's all there is to construction engineering. Just remember, take out, in this case, the support force 0, take it off. Remove the dead weight, take it off. Elongate the cable, force 0, take it off. And that's all there is to it. And if you give these commands to the system in Sophistic, it will give you the runoff forces and the deformations and everything. So that really is the heart of the matter of what we are talking today. And I know, as I said, it's a little difficult to think the construction forwards and then calculate backwards. When you remove something, you have to install it. But believe me, you can do it. I did it. You can do it also. And many other engineers have done it. So, now we go one system further. Instead of a one tower system, we go to a symmetric system. Now, the difference there is forwards, we build the two cantilevers either in parallel or one after the other, but we end up that we have the closure piece and connect it, and then we have put in the right cable forces, and then we have our final stage. Okay, now we have to do that backwards. In order to be able, as we used to say, to open the system, in order to be able to open a system, to open a beam at any stage, we must make the three action forces in this joint 0. Told you before, I can only remove something when I have made the corresponding action force to 0. Now, to take out this piece, we have to make the moment, normal force and shear on each side to 0. Only then can we take it out. How do we do it? First of all, we take out the dead weight. But in this case, since it's a continuous system, we have here some run of moments left, which we also have to make to 0. And now comes the big advantage, if you want to, of a cable-stayed bridge. By pulling at the cables, by pulling at any cable, I can influence any action force at any location. Every cable is involved with every place. Naturally, the cable has the largest influence at that point where it is anchored. But it is a dear illusion if at one place I have a too little moment, that it's good enough to pull at the cable which is anchored at that place and get the moment right. No way. You have always to make a complete matrix with all cable shortenings summed up for this one point. Now here we have, mathematically speaking, 6 unknowns. 3, M and V. Here still is Q, it's meanwhile changed. Q is the German word for shear. The English word is shear also, but it's abbreviated with a V for vertical. I think in the text it's already changed. So, 3 unknowns here, 3 unknowns here. Then we need 6 unknowns, we need 6 conditions. And the 6 conditions are the 6 cable shortenings, 3 on the left hand, 3 on the right hand, which gives us a matrix, which gives the influence of every shortening to every of the 6 unknowns. And then we end up with a set of cable shortenings, which the computer gives us. You can either formulate the matrix by hand, which we did at that time because the computer program couldn't do anything else. But today, if you tell TDV you want these to 0, he carefully does it, but you should know how he does it. It's that way. Now, we then have a set of cable shortenings which reduces these moments to 0 at this place. Moment, normal force and shear. And when that's 0, then we can open the joint. We can tell the computer there is a joint which doesn't transfer M, moment, normal force or shear. And once we've done that, the weight we have here already removed, we can then take it out. And what do we have now? We have 2 one-tower system, what we had before. So, same procedure as last time. We now take off the weight, elongate the cable, and so on. It always comes down at the end to this system, only to get there sometimes requires a little additional work. Okay, now we have dismantled a symmetrical system with a floating crane. Now we come using a derrick, which again takes us a little consideration. So, I have already, I have here on a cantilever system, I have already removed the first part. And now, when we think on site, going forward, at the beginning of erection, we install a derrick, lift the element, move forward the derrick to the new element, next one, cable is installed, and so on, until the last derrick element is installed, and then I take off the derrick. Simple. Okay, what means that thinking backwards? At the end of construction, when on site I remove the derrick, I have to install the derrick. And then I have, with the help of the derrick, remove element, and the first element, move the derrick backwards, next element cables move backwards, until I come to the begin of erection, where I take the derrick off the beam. Just the other way around, calculation-wise, than on site. Now, we have here this system. Just the joint has already been opened without the help of a derrick. I can do that on site without derrick. And now I place the derrick, I install the derrick here on the beam. This is how it shall look. This is the lifting system, and this is a little tieback. And now my bridge feels the weight of the derrick, and I have concentrated all the derrick weight here in one main load in the vertical in the strut. One can do it differently, but that's the simplest. Now, for taking off the first element with a derrick, I have to hang the weight of this element into the derrick here, which means the reaction from the derrick is a force couple, which consists of the vertical component, which comes down here, the main strut, and the moment from the eccentricity of the element. So that is the load the derrick exerts on the beam. And now, if I pull this upwards, theoretically speaking, so much that this moment here, at the end of the element, and normal force at shear, I just talk about moment, becomes zero. Before, we had taken the weight of this section off. Now here we take also the weight off, but not into the air, or onto the floating crane, to be precise, but we hang the complete weight into the derrick. We achieve the same result we want. The action forces at the first joint become zero, so we can open the joint, remove the element. Only that, of course, these loads, for the time being, remain as derrick reactions on the beam. The weight is gone from the beam. That's hanging in the derrick. But the beam feels the reaction from the derrick, from the loads. Again, when we have a floating crane, we have the same derrick reactions, but, so to say, on the water. The beam doesn't feel it. That makes life so much easier there. But if we have the true life and we have a derrick, then the weight hangs in the derrick and the beam still feels the reactions, which I have indicated here with this couple, tries to overturn. Now we have the moment zero. We can open the joint and we can take off then the dead weight, which was until now still hanging in the derrick. It was still there. But now we can take off the weight. And then what remains? Well, it remains the dead weight of the derrick. And in order to go on, we have to remove this dead weight by using the same force upwards, removing it, and then placing it, the same load like here, one step further back. And then it's repeated and repeated until we've taken it all out. I know, it's a little tricky. I bear with you. But it is completely logical. Believe me, and once you know the system, you can sit down and do it for yourself when you have the task. There is nothing to it. There is no myth, or it's pure logic. So, this is now how we dismantle a bridge with a derrick. And with this, we have the main considerations for construction engineering backwards. Now we go into an example for the construction engineering. What I've shown you theoretically now, basically to give you an idea of forward on site, backwards calculation-wise, how, so to say, it is practically done on site. We use the example, what I had before, of the Mannheim North Bridge, which is a cable-stayed bridge between Mannheim and Ludwigshafen across the Rhine River. First of all, we look onto the situation on site. We have built the concrete approach beam, you remember, taking off shrinkage and creep, that was for the concrete approach beam, and now start to free cantilever the steel beam across the Rhine River. And very typical, we take all the beam elements here with a loading derrick onto the beam and then move it forward with a traveling carriage. And we need, for the first element, a little auxiliary pier before we reach the first cable. And then we use a derrick for lifting up the elements. And here they had a special method, a little complicated, to install the stay cables with a high line. Das ist ein Hängebrückenseil, sagt man eigentlich, a high line, from which the new cable was supported. And we go on, and then we have here a little difficulty because the cable distance here was rather big, and so we needed an auxiliary pier temporarily to support this cantilever, which I'm not going into the calculation, but it's basically the same as all these things. And then finally we have built the bridge. I think that's perfectly straightforward, and last lessons, for example, we've gone into that in detail. Now, calculation-wise. Calculation-wise, we do it the other way around. We start with the final completed system, system G. We take off the support, we take off the cantilever. Now we have the little complication that this cantilever, after we've taken out this cable, is a little long, so we need a little auxiliary strut there, but that's just something special. And so we go on, we go on, we go on, until finally we have removed everything. So that is the actual forward construction on site, and that is the corresponding backwards calculation, dismantling the bridge theoretically. And then we come to, after we have checked every construction stage, that A, that it is safe, that the beam is not overstressed, the cables are not overstressed, either because hopefully the sizing for the final stage was sufficient, or in some places, hopefully not too many, we have to add some post-tensioning or steel to cater for construction stages. Only to mention, this is a typical way. We could have left out this auxiliary stay here, but that would have meant considerably strengthening of the steel plates here. So the contractor said, that's very expensive. I rather use a cheap auxiliary strut and some additional work, and by that, then the steel plate thickness for the final stage is sufficient also for this erection stage. One has to balance the costs. You remember, it's for university, it's not usual, I know, to talk about costs. But in real life, it's the name of the game. All we are after here is to get the structure built at minimum cost, plus some other considerations. Very well. But so this is behind, that's how we weigh these things. Anyway, after we have checked that the stresses are okay, we now have to tell the site what we have found in our construction engineering, what the site has to do in every stage. Pull in the cable with this force is a typical. And then we have to tell the site how to check whether the situation, as I have calculated it on paper, is real on site. And for that, we can readily check two parameters. We can check the cable force. Next time I will show you which ways are there to check the cable force. And we can check the deformation by a theodolite, just by surveying. We can check the tip movement, and what is very helpful, by the way, we can check the tower head movement by putting on a plumb bob and load. Now we do it with a laser, but you know what I mean. Down, and you can measure the deviation of the tower head, and that's like a very, very long indicator. That's very helpful. Checking the tower head deformation, checking the beam deformation, and checking cable forces. So that's what I have to give the site in a, let's say, cookbook, recipes. In addition, for the engineers, we always like to give the moment line, but that's just for knowledge. We practically cannot check the moment line on site. So, here we start, and we see at this stage the beam deflection. It's 0.439 meters. With this direct position and everything, this tip should be down, and the corresponding bending moment is here from the auxiliary pier, naturally, is there, and the auxiliary pier force, which we also check, we have that permanently on a jack, on a support nut, and then we can loosen the nut and measure this force. That is an additional force, support reactions, auxiliary support reactions. We can check. And then some notes to the side basically is be careful to check the auxiliary force or the force in the auxiliary pier. That has to be 1,550, and you have to do it all the time because when you move the derrick, this changes and so on. Now, next system, B. We have just installed the forward cable and the backward cable. And we know the force here, it's a little elder publication, so excuse me, use megapond or tons. If you take 100 off, it's meganewton, whatever prefer, or 10 to it's kilonewton. So It's 900 tons or 9 meganewton is the force in this cable, and 915 tons megapond it is in this cable. We see here the picture of that construction situation. We see the derrick here, and we see the one backstay, and we see the one forestay installed. We see the deflection, again, precisely for this situation. With this derrick at this point, when the derrick is somewhere else, we have a different force and different deflections. We must be very, very careful to duplicate on site the complete load situation we have assumed during the calculation. And do not put odd 10 cement sacks somewhere there that changes your whole outcome, and site tends to put odd weights here and there. Yeah, we just need it later. Move it off. Otherwise, you are comparing a different system. I just warn you. And of course, naturally, the derrick is always much heavier than you have assumed in your calculation. I've never had it that a derrick had the weight of what was assumed. A rule of thumb is lifting equipment will weigh 1/2 of the weight to be lifted. If you need to lift 100 tons, assume 50 tons, it's roughly okay, but use a little bit more because it will be heavier. Rest assured, it will always be heavier. It never becomes lighter outside. So that's the basic rule of construction engineering. Assume the worst, and you are probably too optimistic. So you need, of course, to know the installation force at this position for these cables. Just to understand, when it says the Roman notation, it means the complete cable. The complete stay cable consists of various numbers of individual that turns sometimes here up, so 4 to 6, but that's a minor point. Now, at this stage, we have here 9 centimeters deflection only because the cable has pulled it up, and the force of installations, and we see here the tower at point 51, that's the tip, is leaning 13 centimeters to the river. That's, we can check the tip of the beam, 9 centimeters, and we can check with a plumb bob, with a laser beam, that the tower is leaning 13 centimeters. And we can check the cable forces, and as long as all that is reasonably close, well, we're in good shape, and we can go on. Now, we go on cantilevering out the beam until we come to the next cable anchor point and can install the next cable. And we see already here that's a considerable length. You see it here, the situation on site. Well, considerable length means 1.88 meter against the final stage is a deflection, nearly 2 meters down here. Wow, that's what I call considerable, huh? Because we have this long cantilever. Of course, we have a heavy moment, but apparently that's in the range or needed little reinforcement for this stage. And also we have to do something, we have to lower here at the auxiliary pier that down by 5 millimeters, and then we should have 10 meganewton force in it. Okay? All checked, all in good shape, on we go. Now, we have now installed, the difference between the two is, here we have cantilevered the beam, but the cable isn't in. Here we have just installed, we haven't done anything to the beam, but we've just installed the stay cable. So, what happens with the tip? From 1.88 meters down, before a cable installation, we are now 0.8 meters up. So we have a movement of 2.6 meters during cable installation, up 1.8, up 0.6. So if we have large cable distances and a flexible steel beam in concrete, that will all be reduced. Then we can have this here, 2.5 meters going up and down, which is considerable. I mean, that's more than the top of the door. And it's a substantial beam. Well, we have substantial forces there. And now we know we have these cable forces in here. And we have, of course, the backstay, the corresponding to this forestay. We must anchor the force back here into the pier. And here is one word which I'm always very skeptical about and do not like to use normally on site, which is simultaneous. There is no such thing on site like simultaneous. All you can do is to reduce the steps between left and right. So this is meant simultaneous, which means when you stress these two on this side and two here, you are now with a walkie-talkie and you read the gauge reading on the jack, die gauge, die Druckanzeige, and you make sure you do not deviate much. But precise, simultaneous, there is no such thing on site. Forget about it. You can only define maximum differences. If you want to lift simultaneous left and right in order the thing don't even try. Say you may either have the full difference, one up, one down, or so and so much is permitted, but never assume something happens simultaneous on site. Jack stressing left and right is the closest you may come to in real life. Well, we have a certain run of moments, and here we see, and I'm not going into that, you can think about it a little bit, when you install the forces, how the movement of the beam goes, but in principle it indicates, if you add all the four, upstream, downstream, backwards, forwards, 4 cables up, you find out you have the 2.6 meters, the tip is going up. Okay, it goes on. We have the auxiliary stay, and we have a cantilever, here long cantilever, which again now we go down 2.3 meters just before closure. And the next one, we have now installed the most forward cable, then it goes up by 1.3. So we have a movement from 2.6 meters down to 1.3 meter up off the tip by just installing the cable. And you can imagine the cable is inclined, what length, so to say, with a tie rod, you have to stress the cable to get 3.6 meter beam movement up and down. But it's all there, and it shows you for the intermediate stages that you can check the cable force and the tip movement in accordance to the cable installation. Finally, we cantilever out the beam to the other side. Then it goes up, I think, what is it? One meter something. Well, we are not excited about that. We had bigger deflections. Of course, here we have a big negative moment to the first goes on. And so then we do put in here the final one, and we are there. Here it is, the final bridge with the desired run of action forces and the required geometry. And as I said before, We then go on, check all the geometry and check all the cable forces. And when we have done it right, calculated it right, and the site has done it right, then we're just there. We're quite happy. We can open a beer. If not, we have basically only the chance to pull at the cables. And that's always some compromise, because either you get the actual forces, cable forces right, then you may off with a gradient, or the gradient. So you're not happy, and that's what I mentioned before. It's a little point of honor for us construction engineers for cable-stayed bridges to end up without re-stressing the cables. So if you do it right, I was lucky. With my cable-stayed bridges, I didn't have to re-stress, so I'm quite happy about that. But I know others who were, what I say, tuning the harp, Stimmen der Harfe, tuning the harp considerably. So try your best. Well, that's the first part of today.